Okay, so here we go into the section of our presentation where we look at the actual interpretation of a DNP message. And this is where, just like we did with our Modbus exercises, we'll be looking at our DNP breakout sheet, that one large color print, and the object library. Now, to begin with, all you'll need is your breakout sheet, because it's not until we get all the way down into the last part of our interpretation where we actually look at the data objects that are being requested or responded with that we actually would need the object library. So to begin with, you should definitely have your breakout sheet. So first thing I want to do is just go ahead, and when we look at the breakout sheet, essentially what the breakout sheet is doing is, if you start at the top left-hand corner of the breakout sheet, you're starting with the DataLink header, and when we look at interpreting a message, we start at the lowest layer, that is the DataLink layer, and we essentially move our way up towards the application header and take each layer at a time and interpret it. So you would essentially start at this point and work your way down the stack till you've interpreted the whole message, whether it be a request or a response. And of course then that means that it starts up here with the 10 byte data link header. Now, some DNP messages are data link layer messages only. That is to say, they're only 10 bytes long in total, and they're essentially just checking on the status or establishing that logical link between the master and the outstation, or the master and the slave. And I think I mentioned that before. It's kind of like more like a ping in a network that is just verifying that there's a connection and that the outstation is there and there's connectivity between the two devices. So even though there's some messages that are data link header only, and you'd only need to go as far as interpreting that first 10 bytes, there's obviously other messages that are doing more than that, and they're retrieving object data, binary inputs, analog inputs, and so on. And then you have to work your way farther through the breakout sheet to get down to the transport header, the application header, and essentially the objects that you'd be looking up in your object library to find out specifically the type of data that's looking to be written or looking to be read, or to freeze that point, or to directly operate that point, or things of that nature, which is all in the function codes from the master. So this is where the master says whether it wants to read or write a value, freeze it, operate it, and so on. So this is kind of in general how we approach using this this breakout sheet. Now, the other thing to understand too is all of the values we'll be working with as DNP raw messages are all in hex. Just like with Modbus, we look at them as hex values corresponding to the ones and zeros in the message, and we'll do decimal conversions where necessary in order to give it meaning and in order to understand what the message is trying to accomplish. So I just kind of wanted to start with that. So very first thing we would look at is the data link header here as the 10 byte value on the top, and then our presentation will go through finding its way through to determine the transport header, which we would interpret using this information, the application header doing this using this information, and then we'll get to the object header where we move more into using this to understand the object header. So I just wanted to kind of start with that as an understanding of how that's going to be used as we go forward. Okay, so we're talking about DNP messages here. If we take a look at this slide here, this is a DNP request. This is a request message in hex. And down here, this is the corresponding response to that request. Okay, now initially it probably looks kind of scary in that there's a lot of bytes of information here. But I guess just to kind of put your concerns at ease right off the bat, I'll just let you know that as far as the response goes here, in this course, we don't go all the way to interpreting this whole response. In a course I took, we did. We interpreted it all, and we needed another document that was going to describe exactly how each one of the objects in this response were reported back. And that's a document about 1.5 inches thick, and it's a long, arduous process in order to interpret all that. So as far as this course goes, we've always said and always set our limit to, if you will, interpreting up into only the first object header in the response message. So if soon enough we'll realize or find out that it's easy enough to determine this is the first object header. So that's the first object header. And you'd only be required to interpret a response message to that first header, because what happens after that is we have all this object data, and in order to know how to interpret that object data, we need to have that other document and really drill down into it in order to interpret all that. So I just wanted to kind of set that off at the beginning. So back to this slide, just wanted to mention a few more things. When it comes to the message you see here, it's laid out much like what you would see from a protocol analyzer or a communications test set like ASE. It automatically, does some initial sort of parsing of the message to break it down into its layers. So notice how there is no coincidence that this first part of this message that you see here is 10 bytes long, right? So if you look at the first line, you can see this is 10 bytes long. Well, really, that is your 10 byte data link header here. And so when it comes to the lines that are and the way they're shown, it's kind of helpful because it just doesn't show a long string of hexadecimal values. You can clearly see that's 10 bytes, that's the data link header, and then you'd move on to another 2-byte value, which is the transport header, another 2-byte value, which is the application. Then you move into your object headers and carry on with the message from here. So that's the same when it comes to the response. What do we see? A 10-byte data link header to start every message. Then you see the transport header. Then you see the application header, which for a response is 4 bytes long instead of the 2 bytes like you saw in the request, and then carries on with object data. But further to that, notice how it's broken down into multiple lines for a large message. The reason it's broken down like this is because these are all 16 byte data blocks. So it breaks it down into 16 byte data blocks. And when it comes to all of the bytes that you see in this message up until the last 2 bytes, you'll be able to count 16 bytes there. And every 16 byte data blocks ends in a 2-byte CRC. So just wanted to kind of give you an overview of how messages are displayed when we go to interpret them. They're displayed with that format or that manner First line is always the data link header and 10 bytes long. Moves down to the second line, starting with the transport header, application header, ending off with the object header. But if it's a larger message, it doesn't just give everything one after the other and end with a 2-byte CRC. It only displays it 16 bytes at a time, because a DNP message is formatted that way into 16-byte data blocks, and larger messages are broken down every 16 bytes, another CRC, another 16 bytes, another CRC. Of course, if it doesn't require a full 16 bytes to end the message, like what we see down here, then it'll just show the number of bytes that are needed to complete the message, and then of course, as always and every time, end with a 2-byte CRC. Okay, so that's just kind of an overview of that. All right, so this is indicating the DNP frame format, and just like I mentioned, you've got your 16-byte data blocks, and every 16-byte data block ends with a 2-byte CRC, and you can see that carries all the way through until you've reached your maximum number of bytes. Now, the maximum number of bytes we said was 255 bytes. Okay, same as Modbus, same as Ethernet. The frame size is 255 maximum. Now, we can actually figure that out when we look at what we're seeing here in terms of all the bytes in this this message, because this is indicating a maximum message. And notice how it says there's 15 data blocks, each one of them with 16 bytes of data in it. Right? So if you were to take 15 blocks and multiply it by 16 bytes, you're going to get 240 bytes. Okay, so that takes care of the counting of all of these. But then of course you have the 10 bytes at the end here it's talking about, which is finishing off the message. So now we've got to add 10 bytes from that last block. So that gives you 250 bytes. And then we have to include the bytes in the data link header. Now, the thing is as it turns out, these guys here don't count. So that means what's called the length byte doesn't count, the 0564 doesn't count. It's only the remainder of the message that counts. And there we have 5 bytes there. And so that 5 bytes is our last 5 bytes added to our 250 bytes here. We just add 5 bytes. And you have your 255 byte maximum. Okay, so when it comes to that maximum frame size of 255 bytes, what we need to understand is none of the CRCs are counted in that maximum value. So you can just shave them right off the total amount. So it means that in reality, when you include CRCs, you're going to have a much bigger byte size for a frame, but it's that 255 is really the usable bytes in the frame. So it's the 5 here from the data link header. It's the 15 to give you, and the 10 in the last one to give you a total of 255. So when it comes to DNP, of course we have the physical layer that every protocol is going to share. Oh yeah, and by the way, you guys may be sort of wondering, what's this FedEx truck doing in these analogies? Essentially, this is an analogy of a FedEx shipment, and how the labeling of a FedEx shipment in order to deliver it to the other end is involving waybills and addressing and weights and measures and number of packages and things like that. So it's kind of using a FedEx shipment as an example to relate to this all. And I think you'll kind of see where it's going once we go forward and look at the different layers in the DNP3 message. So when we're looking at the physical layer, we know all protocols are going to share a physical layer to connect the ones and zeros between the two devices, whether it be a point-to-point or a multi-point network. When it comes to DNP, it's always a asynchronous connection. So remember, asynchronous connection has the synchronizing bits embedded right into the streaming data. And so when it comes to DNP, we're talking about 8N1 connection. Okay, no need for parity when you have CRCs in your protocol. So we've got 8N1, 8 data bits, no parity, a 1 stop bit for an asynchronous connection. You can have different baud rates. You can communicate it over dial-up satellite, RS-232-45 most commonly, or Ethernet. Ethernet being LAN, WAN, TCP, IP. So really at the end of the day, we know that physical layer is the pathway by which the ones and zeros are transferred back and forth between the two devices. And describing the meaning of the ones and zeros is determined by the protocol itself. And in this case, that would be DNP. So when you're looking at the data link layer, this would be the first part of the DNP message of which we can use our breakout sheet or our message structure sheet to interpret the meaning of the hex values in the message. So if we look here, we're looking at, again, that request. So this part from this is from the very first slide we looked at. This is the request from that slide. It means that we already established the fact that the first 10 bytes is something called the data link header, and we would now look at that 10 bytes and its hexadecimal values and use the breakout sheet to break it into its different boxes, just like we did with Modbus. Remember with Modbus, when we used our handout, we had our empty boxes that were determined by the formatting of the message based on its function code and its format, and you just drop the hexadecimal information into those boxes. It's the same idea here when it comes to DNP. So if we were to look at using our breakout sheet, we would have determined the size of all these boxes, right? The box size here is all determined by our breakout sheet, right? So first of all, we have a 2 byte value, then we have a 1 byte value, another 1 byte value, 2 byte value, 2 byte value, and we end with a 2 byte CRC. So you could think of, other than the hexadecimal information that you see here, this whole process started by referring to our breakout sheet and determining the size of the boxes in that first 10 bytes of that data link header. And notice how it's a total of 10 bytes. Okay, so this is just the first part of the message of which we're interpreting. So the first 2 bytes of that data link header are something called the start bytes. It's always a 0564 value. That 0564 value is our start octets. Now that's the other thing too, is DNP sometimes calls bytes. A byte equals an octet. Okay, so we know a byte is 8 bits, and DNP sometimes refers to 8 bits as an octet. So the start octets, or the start bytes, are 0564. That's clearly identifying this as a DNP message. Now there's all sorts of rumors or things that I've heard as to why we have 0564. Rumor is the designer's birthday of his daughter was May 1964. But in any case, that is clearly identifying our header, our data link header, as a DNP message. Kind of a, and this is where the analogy has been for FedEx, is that's the label on the outside of the package. How do we know it's a Pure Layer, a FedEx, a Canada Post package? Well, it's by the markings or icon, if you will, on the box. And you can consider that to be the DNP icon on this message, indicating, hey, this is a DNP message. It has start octets or start bytes of 0564. Okay, then we move on to what's called the length byte. So that would be the third byte of the object, or sorry, the third byte of the data link header, and it's a 1 byte value, right? Now, this is where, because this isn't a code, we could simply say 0564 is a code. Okay, we don't need to convert that to decimal. But the length byte, which is in hexadecimal, is indicating the numbers as we know them in order to count the number of bytes in the message. And so this is an example of where we have to convert this 0x14, the hexadecimal value of 14, to a decimal equivalent. And in this case, that would be 20 bytes in the message, right? So if we look at the length of hex 14, it's telling us there's a total of 20 bytes in this request. Now, here's as good a time as any to look at this. It's saying we have a minimum of 5, but a maximum of 255. So we have hex values of 05 through FF. What's the maximum value of a hex number that could be taking up a 1 byte? Well, it would be when they're all ones, right? So that would be, that would be a binary value, That would be a binary value of when that 1 byte is all 1. So it would be 1, 1, 1, 1, 1, 1, 1, 1. All 8 bits are 1s, making that FF, which is equal to 255 base 10. So why a minimum of 5? Well, the smallest DNP message that's possible is a data link header message only, and that's where I talked about that kind of being like a ping. And when we only have a data link layer message only, it means that the usable bytes within that message are only the data link control byte, the destination address, and the 2-byte source address. So altogether, that gives us a total of 5 bytes, because remember, the CRCs don't count, and the start byte and the length byte don't count either. So notice how it says the length calculation does not include 0564, so that's not included. The length byte itself, that's not included, or any of the CRCs. So we would not include the CRC in that message, and the length would be a total of 5, which is the minimum number of bytes in a DNP message, and that would be the result of a data link header message only. Okay, so hopefully that makes a little bit of sense. Let's look at this example that we have, where on the very bottom here it's indicating that request message. It said the length was 20 bytes, okay, because we converted hexadecimal 14 to 20. So if we were to count this all, and we know we would not count 0564, we won't count the length byte itself, we won't count the CRC at the end of the data link header, and because every DNP message has to end in a 2-byte CRC, we wouldn't include the 2-byte CRC at the end here. So it just means we would count everything from there, of which we know this is 5 bytes, and now we just count the rest. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So you can see how there's a total of 20 bytes for this request, and that was indicated by the length byte. Okay, so just remember that length byte is going to indicate the size of the DNP request or response, but it does not include the start octets or the start bytes. It does not include the length byte itself, and it doesn't include any CRCs in the message. And this is where the analogy has been drawn to a FedEx waybill, in which the weight and the dimensions of the package are listed on the waybill. Same idea here. The length byte is indicating the weight and dimensions of the DNP message, if you want to think of it that way. Okay, so that's on the there. So then we come to what's called the DataLink control byte. So the DataLink control byte is really saying, okay, what is it that we want to accomplish with the DataLink header? Now, this shouldn't be confused with what we want to accomplish when it comes to the application header, because the application header is where we specifically say the type of data that we want to read as an object group, and whether we want to read, write it, freeze it, or operate it. But this is the indicating what is the function of the DataLink header. So this has got to be, you know, mentioned. Is we're not going to find reads and writes of object types here, but we're gonna be indicating what it is the DataLink header is trying to do. And this is really whether we're looking at confirming the message at the data link layer level going out. We're going to do a reset link, test link, things like link statuses and so on. And so when we send out a data link header message only, the master wants to know that it's been received, and it'll be looking for a confirmation from that data link header message only. And so there would be an example of confirmed service, because it wants to confirm that the outstation received it. But what would be an example of unconfirmed service? Well, if I'm asking for object data, I don't need confirmation that you received my data link header. So this would be when you're looking for user data or objects. When you're looking for objects or user data, it would be redundant to look for confirmation at the data link header level, because you obviously know the data link header has been received because it's part of every message. So you can move your confirmation, if you will, down the stack and go with unconfirmed service when it comes to the data link header. So in the FedEx analogy, that's where you're looking at your type of service for your delivery. Does it need a signature at the other end from somebody? Otherwise it won't be delivered. Is it insured or uninsured, and so on. So it's the details of confirmation or security, if you want to think of it in that way, in terms of the FedEx package being delivered. Okay, we're going to just finish off this video with the data link header, but let's break it down here now into this destination address. Now, this is the first point at which we really got to watch out here, guys. But as long as you're following your DNP breakout sheet, you won't have an issue. If you start to take things for granted, that is to say, you get familiar enough that you start being sloppy, maybe you might say, you might miss this. This is what we need to understand, is in DNP, all 2-byte values are flipped. So let me kind of define what I'm talking about here. 2-byte values, doesn't matter what they are. 2-byte address, 2-byte point data, 2-byte CRC. Every 2-byte value is flipped. So that means in the raw message, what you end up having is the least significant byte of the message first, the most significant byte second. So that's really going to catch you if you're not aware of that. And if you go back to your breakout sheet, you can do that right now. You can even pause the video if you want. You'll see that's exactly the way it's shown in your breakout sheet. This is the most significant byte of that address. This is the least significant byte. Now, be aware, that's talking byte, not bits. So, when we reassemble this address in order to interpret it, we have to do the flipping. We have to flip it back to interpret it. So that means here the destination address would be interpreted as 0x0001. Notice how we flipped it. Okay? So that's something that can really get you if you're not on top of that. And that is, remember, all 2-byte values need to be flipped. So that would be a 0001 in hex, which of course is 1 in decimal. But let's just carry on for a minute. We'll do that later on here too. But that means if that's a 2-byte source address, that would have to be flipped as well, wouldn't it? So the source would be flipped and it would equal 0x0064. Okay, and a matter of fact, in order to get the right CRC value, you'd have to flip that as well, because the actual CRC calculation would be D667, because it's a 2-byte value. All right, so when it comes to that destination 2-byte value, what are we talking about? We're talking about where is this DNP message going to, its destination. Where is it going to? So it's the address that it's going to. This will be for a request. This is obviously going to be the server address. So this would be the server address. You can see that we have a maximum of 65,520, or the hexadecimal values that you see here. But if you were to look at a 2-byte value, you know it goes up to 65,535, but we have reserved addresses at the top here. Okay, so that's the FedEx analogy. Where's the package going to? Okay, so you get the idea, I think, here. If you look at the next 2-byte value, it has to be flipped, right? So this would equal a 0x0064 value in hexadecimal, which works out to decimal address 100. So this is actually coming from a device with an address 100, and that's, if this is a request, this is going to be the master address. Master address is 100, and it's sending a request to a server number 1. And because DNP allows multiple masters, we have to have a unique address for the master now. So every DNP message is going to have both a server address and a master address in it. It's just that when it comes to requests, the destination is going to be the server, and when it comes to a request, the source address is going to be the master. Okay, so it's the from address, right? We have the same range of addresses that we did for the servers, and we have reserved addresses, right? Okay, so the addressing is the same, but when it comes to DNP, we also need a master address as well as a server address. In Modbus, we only had server addresses because you're only allowed one master. But in DNP, we need to uniquely identify that master by an address. Okay, so the analogy is, who's it from? What's the return address on that package? Okay, then the last part is our 2-byte CRC, and that is our cyclic redundancy check. That's our code that's calculated based on a calculation with the CRC calculator, and it doesn't really matter for the purposes of our exercises, but remember, this is a 2-byte value once again. So if you were to actually use a CRC calculator to calculate or confirm this CRC value, if you hit equals, you wouldn't get 67D6, you would get D667, because again, it's a 2-byte value that has to be flipped. So just so you understand there. And so this last part is for the FedEx is the checksum, or the checking to see if there's online confirmation using scanners and things like that to make sure the delivery was delivered. Okay, so we looked at the DataLink header, and we talked specifically about the start octets or the start bytes, the length byte as a 1-byte value, the DataLink control byte as a 1-byte value, and the destination and source addresses and the 2-byte CRC all as 2-byte value. Don't forget, these have to be flipped. Any 2-byte values have to be flipped before they're interpreted. So that's just kind of a view of what we looked at when we looked at this DataLink control. Now, this DataLink header. Now what we're going to do is look at the DataLink control byte, which is really the part of the DataLink header that's indicating what are we trying to do with this DataLink header besides establishing the lock. So when we're talking about that DataLink control byte, that's the 1-byte value that takes up the fourth box, or the fourth position, if you will, in the DataLink header. And so in order to interpret it as a bit-by-bit interpretation, on your breakout sheet, you can simply follow over to this breakout piece, or this guide here, that's going to look at each and every bit within that DataLink control byte to determine things like the direction bit, the first one. Is it from master, or is it from the remote? Is it a primary message or a secondary message? And the remaining of details that are found in it. But I'm going to keep it simple. And I'm going to suggest to you that the easiest way and most effective way to look after the DataLink control byte every time when it comes to interpreting it is to simply go right to this table right here. And what this table does is essentially summarizes everything that's going on here. And it's much, much easier to determine everything you need to know right from this larger table. So as an example, if we look at the direction bit, the direction bit being a 1 is going to mean that it's from the master. If the direction bit is a 0, it means it's from the remote. So essentially it means that if we take a 1-byte value and we make the most significant bit a 1, that'll make that value 8 or above, just like we saw in a Modbus exception code. When the most significant bit is 1, that's going to make the hex value 8 or above for the first digit. If you were to take a closer look at this DataLink control byte table, look at how all of the DataLink control byte values as a hexadecimal number are 8 or above when they're from the master. And why is that? Because that means that the direction bit is a 1. Sorry, that's not the greatest there, guys, but that means the direction bit is equal to 1. If we look here, where the DataLink control byte and its hexadecimal value, its first number is less than 8, 0 through 7, that indicates the direction bit is a 0, and that's indicating it's from the remote. So then, as we move forward, further questions like whether it's a primary or secondary message can be found by using the table this way. So as an example, if we looked at unconfirmed user data from the master, that's a C4, and it's a primary message. You can see that it's a C4 and it's a primary message. If I look at confirmed user data down here, notice how that's also from the master for a D3, and it's a primary message. Corresponding from the remote would be 4.4 and 5.3. So you see that one of them is a primary message for unconfirmed user data from the master, and the other one's from remote. And what was the difference? Well, the most significant bit, the direction bit, was a 1 for every one that was in the from master column. Okay, so I just wanted to kind of direct you as to where and how to use your breakout sheet when it comes to DLC. Just go directly to this table right here. Just go directly to that. Okay. So if we're looking at the DataLink control byte, again, we've got that direction bit we talked about. That direction bit is either a 0 or a 1. And if it's a 0, it's from the remote. This says where it's from. And if it's a 1, it's from the master. And then we have something called the primary or secondary message. When it comes to DNP3's DataLink headers, any message that goes out initializing a DataLink header is a primary message. Now the thing is a return message can also be a primary message unless it is confirming a primary message being sent by the master or by the remote. And so secondary messages are responses at the data link layer to primary messages that are looking for confirmation. So that needs to be understood. If a primary message goes out from the master, and it's not looking for confirmation, what comes back is another primary message. So it'd be primary, it would be primary going out, primary coming back. But if a primary message goes out and it's looking for data link layer confirmation, then what you're going to have is a secondary message coming back, because that's saying you were looking for confirmation at the data link header, I'm providing it. When we do involve confirmations and things like that, then we may involve other bits, I guess I'm going to say, within the data link control byte, so that we're not misplacing confirmations and things like that. And this is where the frame count and data flow bits come into play. Essentially, guys, we're not going to get into a bunch of detail when it comes to all that. We're basically just going to leave it such that if you ever wanted to know specifically whether that FCB bit was 0 or 1 and the data flow control value, you can simply go back to that table. And I'm going to show you what I mean when we go back to that table. If we go back to this table, notice how it gives you all those values of data flow control and FCV right in that part of the table. Right there tells you those answers, right? And over here, you can even see there's additional information. Notice how in this part of the table it says FCB, frame count bit, is equal to 0 and is ignored. Frame count bit is equal to 0 and is ignored, right? And that means that there wasn't any essentially confirmation process going on, so none of those bits needed to be considered when it comes to any level of confirmation from the data link header. So guys, I guess if I'm just trying to sort of scale what's required of you for this course, it's really just that you're able to go to this table when you see a data link control byte and answer questions like, is the FCB high or low? Is it a primary or secondary message? Is it from the master or from the remote? What's its function? And all that. You're not specifically required to know the exact purpose of each one of those bits. You just need to know how you'd use the table to interpret it. And don't forget, if you want to know more information about any of that, you can just go to dnp.org and do a search for something like define the meaning of the frame count bit, and things of that nature. It'll give you all the information you need. Okay. So again, I talked about these primary, secondary messages. The secondary message is a confirmation from the other end when the initializing device was looking for confirmation. So if we look at the first example, when the request went out from the master, this was a primary message that was going out from the master that was looking for a confirmation of the data link layer. And so what came back was a secondary message. If we look at the second example, this is where the initiating device or the initiating end was a remote. So it sent out a message as a primary message looking for confirmation at the data link layer. And so what would come back is a secondary message from the master in this case. This would be an example of what would happen with an unsolicited message. Primary message would go out and it wants confirmation from the master. Okay, so again, guys, this is really the table you're going to find on your breakout sheet. And I would say this is the one where you're going to go to in every example in order to answer any question you want. So what we're going to do is we're going to use this in this next slide right here. So here's an example of interpreting a data link header, and it's interpreted using your breakout sheet or your handout. So where does it start? Well, it starts by understanding that when we use your breakout sheet, we're going to the 10-byte data link header, and we're breaking it down into these boxes that we see here. A 2-byte value, a 1-byte value, a 1-byte value, and then two 2-byte values, and then we end off with a 2-byte CRC. So if we look at this then, what would that mean? We start with a 2-byte value, of which we know our breakout sheet tells us it's a 2-byte value, a 1-byte value, a 1-byte value, a 2-byte value, another 2-byte value, and a 2-byte CRC. It's that simple. We just go to our breakout sheet to get that information. Then you interpret it one by one. Start octets or start bytes, 0564, identifying it as a DNP message. Then you have your length, of which we know is 20 bytes of user data, of which we confirmed earlier by getting rid of the the CRCs, the length byte, the 0564. So don't forget, in this 20 bytes, we have not including 0564, the length byte, or any CRCs. So if you were to count up like we did previous, you'd see there's 20 bytes to this request. Now, let's take a look at our DLC of C4. What we're going to do is we're going to use this table like we talked about, and we're going to look up C4. C4 is going to put us right here. Okay, so what does that tell us? Well, it means that we've got unconfirmed user data, and what that's saying is there's no confirmation needed at the data link layer because you're looking for user data. So all of the confirmations will come through layers that are higher up the stack, like the transport function and the application header and so on. So we unconfirmed was all that was necessary here, based on the fact that it's a message that's going to certainly have more layers than just the data link layer. But what else can we say? Well, we can certainly say it's from the master, because we can see its hexadecimal number is 8 or above. So it's from the master. We can say it's a primary message. And if we wanted to know if the frame count bit was 0 or 1, we can see the frame count validation bit is 0. And you can answer any question you had from there using this table. So this is just asking you to use your breakout sheet and to give this a try again, going through all the particulars of it. If you want to find out the answers, of course, you can just find it here. Notice how this has been flipped, right? We had to flip it before we interpreted it. So did we have to do that here? And that's how we got a decimal master address of 100 and a remote of 1. Okay, here we're bringing in the transport layer. Now remember, the transport layer is called the pseudo layer because it's only used on DNP messages that are greater than what can be handled by a single data link frame. So when there's a message that's so big that it requires more than 255 bytes, it won't fit into one data link layer frame, and we have to segment it into multiple frames, and we have to assemble those frames properly for it to be meaningful. And the whole segmentation part is being looked after by the transport header. So that's why it's called pseudo layer, because it's not always, the function of it is not always being used, only on larger messages greater than 255 bytes. Okay, but the thing to understand is, as soon as we have a message that is more than just a data link header message, which we said some messages can be just a data link header message, like reset length, more or less like a ping. Whenever we have a message that's greater than that, for sure the transport layer information is going to be present. It's going to be in the message. It just most likely will not be used. So we're talking about segment. Let's just go to our breakout sheet here, and we will look at the transport header. Now the transport header, then we're going to find right here. As the next byte in breaking down the layers. We came from the data link header and moved on to the transport header. In order to interpret it, we just follow this line down, and all the information we need is right here. And notice how it's giving it it's a segment, it's calling it, because we're segmenting a message that involves multiple frames. And so it's a 1 byte value. So a 1 byte value is a total of 8 bits. And so we've got our 8 bits here being listed in that 1 byte value, right? So when we look at coming up with the meaning of that, we're going to just follow it down and find it here on your breakout sheet. So what if we have a DNP message that's so large that it would require 4 frames? So 1 frame wouldn't be enough at 255. The 510 bytes wouldn't be enough for 2 frames. You get the idea. So we would need a total of 4 frames in order to communicate back the response. If that was the case, then that's where the transport header would come in. So we've got one giant DNP message it has to be broken into frames of 255 bytes each. And so what would the transport header look like? Well, first of all, for the first frame, what it would mean is it's the first frame of the message indicated by a 1. It's not the last frame indicated by a 0. And then we'd have some value of sequence number in there, sequence X. Now the reason why they don't have sequence, they don't actually have a number in there, it's because X could be any number. As soon as we have a message that has more than one frame, then that number will increment from wherever it was and will continue from wherever it was previous to that. So if the last message that was a multi-frame message had a value in there of 7, then on the next one, even though it was the first frame, it would go up to 8. So that's the reason why we can't just say the first frame of a multi-frame message is always going to be sequence 1. Hope that makes sense. So then for the second frame, we know it's not the first frame. We know it's not the last frame, so we've got 0 in both those positions. But notice how we add 1 to the sequence. And adding 1 to the sequence is the way the far end knows that, oh, okay, that's the second frame. I know it's not the last one, there's more to come, but it's the second frame because it was X plus 1. Okay, so I think you get the idea. If it's the third frame in the message, then it's not the first one or the final one again, but it's X plus 2. So that's the way the other end knows how to assemble it. That's box 3 of 4, if you want to think of it that way, as far as this shipment goes. Okay, then when it comes to the last frame, that's the fourth frame. We can see it's not the first, but it is the final frame, but it further carries a sequence number of plus 3. So it's the way that you know that that's the final frame of that sequence, is the final one with an X plus 3 value. Okay. So if we look here at this request going out, this was the request that we looked at from the very beginning. If we look at now the transport header, we're going to find that 1 byte of information here. And we know we have a hexadecimal value of C0. Well, if we split this right down the middle, we know that this is equal to 0xC, and this is equal to 0x0. So this is giving us a value of C0. If we plug the 1s and 0s in there, as you can see, that's 1, 1, 0, 0, 0, 0, 0, 0. That means it's the final frame and the first frame. Notice how it's kind of strange the way that the first bit is the final bit and the second bit is indicating the first bit. So it's kind of a little bit confusing that way, but realize that with 1 and 1 there, that's indicating it's the first and final frame. The sequence number in this case is 0. Right, so that's how come we have C0. Now, so just finishing it off here, guys, what are we saying by this C0 transport header? Well, we're saying it's the first frame. And why? Because we had a 1 in the first frame bit. It's the final frame, because we had a 1 in the final frame bit, and we have segment sequence number of 0. So what is this saying? It's saying it is the only frame. And so often when it comes to DNP requests going out, you're just going to see for the transport header C0, 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 C0 in terms of the communications and the polling that's going on, because a master certainly didn't need to send a multi-frame message to get its request across. So you'll expect to see a sequence of 0 and the first and final frame on a request going out over and over. Now later on, when I look at some ASE screen captures, I'll show you how when a response comes back, however, even though it may be only a single frame message like it usually is, the sequence number will go up by 1 every time. And that's just a way of a master accounting for all responses to make sure that every response has been received. If it's missing a sequence number, it says, hey, you know, what happened? I must have missed a frame. So I'm going to demonstrate that later in ASE as far as the screen capture goes. But for now, just keep it that simple. Go to your breakout sheet, look at that 1 byte value, and look for the numbering of the frames as the first and final.